Okay, so let's continue where we left off. It's not too difficult to remember where we left off this time. We left off with the data viz pipeline, so let's jump right into the first data acquisition phase. So this is assignment one. Like assignment one, Project Tycho is the data acquisition phase. So a team of scientists spent many years and millions of dollars collecting this data. This happens a lot, like spending many years, 5 to 10 years, or even longer, and several million pounds collecting data. It happens all the time. It's called data acquisition. Data is generated or acquired, right? Project Tycho is just one example, but there are millions and millions and gazillions of examples. There are examples from medicine, like computer tomography and MRI. Text is an example, walking into a library or a digital library. User input is another example of a data source. Whenever you use your mouse or your keyboard to add information into databases. Simulation is another source of very, very large data sets. That's very abstract. We are actually going to talk a little bit about that later on in the module. Computer-aided design is another one. Videos and images. You don't usually think of videos and images as data, but they are certainly data. So data is generated and acquired, and it's usually some instrument that's generating the data. Usually. There's an enhancement phase, and that's also part of assignment one, where you're shuffling things around. You're putting data into groups. Maybe you're combining spreadsheets together. Maybe you're separating spreadsheets apart for some reasons. But that's an example of data enhancement. Data is prepared or pre-processed. So that's another kind of learning curve aspect to assignment one. Every tool will have slightly different input requirements, how the data needs to be formatted so that the tool reads it properly. That's an example of data enhancement or pre-processing. Other examples include filtering and smoothing, discovering errors and fixing errors. That happens all the time. Filling in missing values or deciding how missing values can be interpreted. Resampling. Anybody heard of that term before, like resampling? We won't go into it in a lot of detail. But modifying a grid representation, for example, deriving new data, right? That's certainly, you're welcome to do that in assignment one, and other kinds of tasks. Data interpretation is a way to fill in missing values. So if there are some missing values, but you can make some guesses as to how to appropriately fill them in, that's data interpolation, and it's a topic that's going to keep recurring throughout the module. Then there's visualization mapping. This is the main focus of this module, how you take data and map it onto things you can see. The basic premise is data is much more interesting and valuable if you can see it. You want to be able to see it. It's so obvious, isn't it? It's so obvious. But yet, most of the data is completely invisible. Like all the data in databases and everywhere, it's actually invisible. And all we're doing is making it visible. It's so obvious. But anyways, visualization mapping results in data being visible. It's represented by geometric primitives. We use this term geometric primitive sometimes. That just means turning the data into a geometry, some geometric shape that we can see, like points, lines, triangles, polygons, cubes, tetrahedra, varying size, shapes, different colors, different levels of opacity and transparency. Right, we learn how to do things like compute isosurfaces design glyphs or icons, layout graphs. For example, some of the tools are graph tools. You can use some graph tools in assignment 1. You might compute voxel attributes like color or transparency. Probably you're not going to do that in assignment 1, but you will in assignment 2. And then finally, there's the rendering. Once we've got all the data mapped to some geometric primitive, we send it down the graphics pipeline, so to speak. That could involve a projection from 3D to 2D. There are things like visibility calculations. You could add shading. Shading is always nice to add to your images. There could be something like compositing. And like Sam asked, animation. Your results could be animated somehow. That's all computer graphics, and you're all experts in computer graphics already, I think, because you all took the computer graphics module. So, you know, that you should be like, yeah, finally, like that part's going to be so easy. And there are some textbooks that are very useful for this module. This is probably the most useful one, Interactive Data Viz, Foundations, Techniques, and Applications, 2nd edition. That has a focus probably a little bit more on the InfoViz side. There's another one that has a focus more on the scientific visualization, but there's overlap. And here's another one that's with a focus on perception, human perception. And we'll be referencing those books sometimes. Any questions about the visualization pipeline? Very exciting. What's your name? Yeah, Alex.
So you said we have to use 5 different tools, yeah?
Yeah. 3 different tools.
3 different tools. 5
different visual designs, yeah.
Yeah, so 5 different visual designs. What if I would have basically 2 same ways of visualizing model, but one will be rasterized, one will be ray traced? So we have technically 2 different rendering techniques.
What was the first one? You said
Rasterized.
Rasterized and rasterized. Yeah, I wouldn't recommend that. Yeah. So you want to have something like, you know, maybe a scatter plot as an example, maybe a parallel coordinates plot, maybe a tree map plot, maybe a matrix chart. And you won't have to worry about ray tracing in this.
I still, but yeah, but it's a kind of different way of.
That's the rendering side. That's like that's not really the visualization side. Let's say that's more like the rendering side of things. But yeah. Any other questions? I can see that anticipation is very high. Everybody can't wait. They're like, oh, I can't wait to start this. I mean, you can start it literally as soon as you walk out because the tutorials are already there. If you want to look at it, you're like, oh, it's free points. It's free points. I go, click here, click here, click here, and boom, there's your map. Like, there it is, a data viz map. And free 10 points. So,
like, how big do the differences need to be in visualizing? So, for like hierarchical data, you could do like tree map, but also circle packing. Is that big?
Just be careful with this circle packing. If it's hierarchical, that's okay. But if it's a standard bubble chart, or it won't get the points you're looking for. But if it's a hierarchical bubble chart, that will get you points. So yeah, a hierarchical bubble chart will get you points, and that's different. It's a different visual design from a tree map. Yeah, but a standard bubble chart is not going to get you many points. And the reason is because it's the same as a bar chart. It's just instead of using bars, those bars are now circles. It's just too simple. Any other questions? So exciting. So exciting. Okay, let's start the introduction part 2. We're not going to finish, but we can at least start. And if there are questions or comments, feel free to interrupt at any time. Anytime. I like being interrupted, and I like it when people ask questions. I find it boring to only listen to myself. I talk to myself all day, every day. It's just boring. I like it. I'm going to actually try to learn the names. It's like Ollie or something.
This is Ziggy. Yeah,
Ziggy.
Close enough.
Okay. I might learn some names. I'm really bad with names, but I might learn some. If you keep asking questions, certainly. Ziggy.
Yeah. So I've been like reading obviously the introduction to this, trying to see if there's a so for the data sets, it says for each description, for each visualization, you've got to say what data set you use.
Yep.
And they will have to be the same data set, or do they have to be different necessarily, or could they be two? You know, like
They can all be the same data set if you like, but they all come from Project Tycho. So Project Tycho has, I don't know how many, maybe 1,000 files on there or something. They have to come from the Project Tycho, and they should have a DOI. Yeah. Does that answer the question?
Yeah.
You can use other data sets too. Like you could add data sets that are not just Project Tycho, as long as the focus is Project Tycho. But you might say, oh, I noticed this Project Tycho is missing like some of these cities. I need to download another file that shows like every capital city in the US to make sure it's there, or something like that. You can add stuff. Yeah. Did you start it already? It sounds like you started. It's fun. Like I think this is fun. Like I like doing real stuff. I like that. I'm a real world guy hiding in the ivory tower. Question? What's your name, Ryan? Ed.
Sorry if you already said.
Yeah.
What is a DOI?
A DOI is a digital object identifier. Anybody heard that term before? Have you ever had this problem where somebody asks you, what file did you use to create whatever it is you created? And then you say, I used this file, but you're not sure if it's really the same. Like, is it the right version of the file, or did the file change somehow, or is it a unique file, or is it a copy of a file, or blah, 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 blah. A digital object identifier makes sure that if two people have the same one, they're using the same data file. Like that ensures uniqueness and correctness and consistency. So it's given for really important documents, and it's very important for reproducibility. So like if you want to share your results with somebody and they need, if they need that DOI to reproduce the results to make sure they're using the same input data, for example. So it's a digital object identifier. Say that 100 times fast. Any other questions? There will be other terms and things and other questions as we go along. It's very exciting. So we're going to talk about data, or at least we're going to start talking about data today. So this module is very data-centric, which is not true about all data visualization modules. Some visualization modules are very human-centric and start with the human perspective and then work their way down to the data. Here we kind of start with the data and work up to the eyes. Like the viz pipeline starts with the data, and then at the end you have the projection to somebody's eyes. But you could flip it on its head and go from the human back down. That would be a little bit more like human-computer interaction. Right? Some important questions we always ask ourselves are, what is the dimensionality of the data? Where does the data come from? Which visualization methods make sense? Some are more sensible than others. Why did the user collect the data? Very important question. So some of you might want to be looking at the Project Tycho website and be like, is there a section that says why they collected the data in the first place and the questions they were trying to answer by collecting the data? What would the user of the data like to learn? Because usually, not always, there's a reason for collecting the data, but sometimes the reason is just because I can. That, like, I'm just doing it because I can. You know, you know, does anybody here collect things? Collect anything? What do you collect? It's Elsa, yeah?
Yes.
What do you collect?
Bricks.
Bricks. Why do you collect bricks?
The old bricks, the ones that are still
The
standing.
historical ones.
Historical
Yeah,
ones.
yeah.
That's really interesting.
Because it's fun.
Yeah.
Yeah, and you can.
Yeah.
Our family, we were conditioned to collect. In my family, this message was passed down, like, you should collect stuff. My oldest brother collected coins. My second oldest brother collected stamps. That was like what my grandparents said, you guys should collect these things. And you know what they picked for me? For me, this is all when we're like 4 years old or 5 years old, right? They chose keys, like they said, Bob, you should collect keys, which do not appreciate and value over time. Anyways, that's not relevant. Data dimensionality. We're going to talk a lot about data dimensionality in this module. The term has different meanings. It's to try to confuse you as much as possible. When we're talking about scientific data and we talk about data dimensionality, we're usually referring to space. So anybody know what 1D space looks like? Any mathematicians in here or statistics? 1D. It's a line, exactly. 2D space. Everybody can everybody imagine? What's that called? Plane, exactly. This is a 2D space. This is a 1D space. 3D space is a volume, like a cube. 2.5D we use sometimes. That is a surface in 3D. It's halfway between. And then there's instantaneous or time dependence. So instantaneous means a snapshot of time. And time dependent means it's changing over time. So instantaneous data would be something like a photo, and time dependent data would be video, and it changes over time. And if you add, that's another data dimension. So if you have time dependent volumetric data, it's called 4D data in this context. Examples include medical data, data from flow simulations, GIS data, and it's associated with a physical phenomena. That generally means it's associated with something you can see in the natural world around you. Right? Then you look around in the natural world, and there's space and possibly time, although that's debatable, but certainly there's space. And those are physical phenomena. You look around, you see physical phenomena. In information visualization, there's no inherent spatial reference, and the term data dimensionality changes. It changes. So if your data is stored in a spreadsheet, then every column in the data set is a data dimension. You could, for example, have a list of cars in a spreadsheet. You're shopping for a car and you're trying to compare them. Every car is going to have like a year of manufacturer, a model name, a manufacturer name, the horsepower, the weight, the color, the retail price, the acceleration, horsepower, and so on. Each one of those attributes, data attributes, would be stored in a column, and that would be called a dimension of the data. So a car data set, we would say, is a multivariate or high dimensional data set. And since there's no space associated with information visualization data, we have to derive a synthetic space. Like, for example, bar charts, pie charts. Those are all man-made spaces. And this includes database, text, spreadsheets, survey data, monetary data, call center data, so on. We also have different data characteristics. This will be our last slide. So we have scalar data. Those are numbers. That's the data we're familiar with, numbers. Anybody remember what a natural number is? It's kind of a good pub quiz question. Yep, exactly. What's your name?
Alex.
Alex, well done. Yes, the numbers that you can count on your fingers, for example. Integers. Difference between natural and integers.
Natural integers. So it's natural numbers, opposite of natural numbers, and zero.
You mean, what do you
Negative.
mean by opposite? Okay, yeah, that's right. So integers include negative numbers, exactly. How do you know this, Alex, by the way?
I learned it at school.
Good, you went to a good school.
Thank you.
Rational numbers, so that's a less common.
Let's do that.
Well, I did learn this in school, I still remember. I think, the Chinese students, they're always very happy about their mathematics training. That's what they tell me. Any Chinese students want to tell us what a rational number is? Whenever I talk to the Chinese students, they say, we are mathematicians. Boom. Which I believe, by the way. I do believe that. Any Asian students want to? Rational numbers are numbers that can be expressed by a division or a ratio. Yeah. Then there are real numbers, so that includes all numbers between the integers as well as the integers. And then complex numbers that have the real component and the imaginary component. We're not going to talk about those very much. But those are all different kinds of numbers. We're used to numbers. There are also things called vectors and tensors, which aren't just simple numbers. Anybody know what a vector is? I bet some people here know what a vector is, but they're just too afraid to say it. Sam?
Is it just a coordinates in more than 2D space?
Say it again.
It was what?
Coordinates in more than 2D space.
Coordinates in more than 2D space. You could have a 2D vector. It's possible.
Instead of numbers and 1D, I think.
That's right. Numbers are 1D.
Yeah.
And vectors are
2D plus.
2D. Yeah, that's right. Or 3D. Yeah, generally. So they're a scalar, which is a number, but with the added information of a direction. So they have a direction. When you watch the weather report, that's an example of vector field visualization, actually, because things are moving in a direction. You want to know where the snow is going to come, how it's going to navigate around Swansea. You'll never get here. Then you have tensors. Tensors are similar to vectors, but they're not exactly the same. It's multiple vectors in some ways, but they have no direction. They just have an orientation. We won't talk very much about tensors. There's non-numeric data too, though, like text and letters and nominal values, like first, second, third, and so on. So don't forget about text. That is data. And text is really challenging. It's very challenging to visualize, actually, because it is uncertain. If I tell you a word, there are multiple interpretations of that word. And there's a lot of uncertainty associated with words. There are also multi-dimensional or multivariate attributes, like this goes back to this car and the spreadsheet of cars. Imagine a spreadsheet of cars if you're shopping for a car, and every attribute of the car has a designated column. Right, like car type, manufacturer, year of manufacture. These are all the things that you look at if you're going to buy a car. Right? How many rusty spots does it have, and so on. The price and the number of cylinders and the horsepower. And we also think about the data dimensionality, right? What the range of values stored in the data is. That's very important. How big it is, how it's distributed, the scale and the size of the data, and how many data samples. So these are all very important things that you guys will be looking at as part of assignment 1 as well. Any questions about that? These will all be recurring themes over and over again in the module. This is just an introduction. Okay, I guess we'll stop there.